Hello everyone. Today we're starting on the section Applications of Vectors. In this section, we'll learn about how to use vectors to measure physical quantities and how to find out things about physical quantities with vector algebra. So, let's just review vector sums for a bit. The vector sum of a number of vectors is a single vector, a plus b, the resultant vector. So, it has the same effect as all of its components acting at once. If we add displacement vectors together, for example, we can find an object's final displacement. So if this pink vector is displacement to the left and the blue vector is displacement down, the green vector, the resultant vector, is our final displacement after we've traveled through both of the other vectors. Now, let's put this into a real-world scenario. An athlete runs 10 kilometers north, up there, along a straight road, and then turns 5 kilometers and runs 5 kilometers east along another straight road. So this is pretty nice for us because it means we get a right angle triangle. Those are fairly easy to deal with. His final displacement can be found by adding these two vectors together. That is, by adding the 5 kilometer east vector to the 10 kilometer north vector. This gives us the yellow resultant vector. Well, let's take a closer look at that resultant vector. The magnitude is given by c squared equals a squared plus b squared, which is, of course, Pythagoras' theorem. So we can substitute in the lengths of the triangle as 10 squared and 5 squared, and find that c squared has to be 125. So, taking the square root of that, we can find that c is the square root of 125, or about 11.818 kilometers. So that's the magnitude of this yellow vector here. About 11.2 kilometers. Well, what about its direction? Well, we can find that out with trigonometry. And once again, right angle triangles are very useful for us here. So, our direction, the tan of theta, where theta is this angle here, is given by opposite over adjacent, or 5 over 10. This, of course, simplifies to 1 over 2. So, using our calculator, we can find the inverse tan of 1 over 2 is equal to about 26.57 degrees. So that's this angle. And if we're using a compass bearing, this is of course north, 27.5 degrees east. So it's important when we're writing down bearings to remember whether we're using bearings true or whether we're going north to east or north to west, or whether we're measuring from another object or angle. Now, what about vector differences? Surely we could use those too, somehow. Well, the difference between two vectors can be found by subtracting the initial vector from the final vector. We've learned about this already. So this finds the vector that adds the initial vector to produce the final vector. So what this means is that if, for example, we have a cricket bat hitting a cricket ball, we can find the exact change in velocity that the cricket bat made when it hit the ball. So here we have a cricket ball traveling north at 30 meters per second, pretty fast, and struck by the cricket bat, so it ends up traveling exactly northeast at 30 meters per second. So we can find the change in velocity of the cricket ball by subtracting the initial vector, that is this white vector here, from the final vector, which is the yellow one, of course. So let's do that. Here we have a diagram of what it looks like after we subtract the initial north vector from the northeast vector. Remember, the final vector was this yellow one pointing northeast, and the initial vector was originally pointing north, but after subtracting it, it instead points south. So to find the direction, we need to work with a few angles. So we know that this angle is 45 degrees, because of course that's the angle between north and northeast. And here we can find a little right angle triangle. Or perhaps we won't do that yet. The top angle of the triangle is 45 degrees, of course, because of the alternate angles. And so we know that the bottom two angles must add to 135 degrees. So the value of the angle of each corner is half of 135. And so to find the angle from north, at which the pink vector is at, we can simply add 45 degrees with 135 on 2. This evaluates to be 112.5 degrees east of north, or 112.5 degrees true. Well, what about the magnitude? That's a little bit harder. So here we will need to draw a right-angled triangle, because with right-angled triangles we can use our trigonometry to solve the problem. So as we have a right-angled triangle here, and this distance we're going to call x. So our edge of the right-angled triangle here will be x over 2, which I'll write there. Now this top angle is half of 45 degrees, 22.5 degrees. As we know, the length of this vector is 30 meters per second. So now we know the hypotenuse and the angle of a right-angled triangle. Using sine, we can find the opposite side. So sine of an angle equals opposite over adjacent. We have x divided by 2 over 30. So using a calculator, we can evaluate that. Well, first of all, we simplify, of course, to find x equals 60 sine 22.5 degrees. And using a calculator, that evaluates to 22.96 meters per second. And so, from that, we found the total change in velocity that the cricket bat made on the cricket ball. And that's this pink vector here, which has a bearing of 112.5 degrees true, and has a magnitude of 22.96 meters per second. And so this doesn't have to be done just with velocity. It can also be used for things like forces, which we'll learn about a little later on. Now, onto frames of reference. A frame of reference is a set of axes that we measure things relative to. So we use a frame of reference to determine what is stationary. Most of the time, we use the Earth as our frame of reference, and we say the Earth's surface is what is stationary. Everything that is moving relative to the Earth's surface. But if you zoom out a little, this isn't always right. Because of course the Earth is orbiting around the Sun at 30 kilometers per second, which is, quite fast. So the ground we're standing in isn't really stationary, at least compared to the Sun. But then if we look at the Sun is orbiting around the center of our galaxy at a much faster speed. And so the actual speed of the surface of the Earth is the speed of the Earth's rotation plus the speed of its orbit around the Sun plus the speed of the Sun's orbit around the center of the galaxy. And, well, the galaxy is moving rapidly with respect to other galaxies, so which one is right? Well, the answer is you can't say which is right. There is no absolute rest frame in the universe. You can't just pick a point in space and say, this point is absolutely still, because there's no way of telling whether it's moving or not. And in fact, relative to various different galaxies, it will be moving or it won't be moving. And so the fact that there is no absolute rest frame in the universe means that we must always measure velocity relative to other objects or other frames of reference. So let's consider two objects moving with respect to a frame of reference, like this pair of cars here. The velocity of one relative to the other can be determined by subtracting the velocity of the observer. So have you ever noticed how if you're out driving on the highway or being driven on the highway, you'll notice the car in front of you doesn't really seem to move much. I mean, it might move slowly towards you or slowly away from you, but it's mostly stationary, really, from your point of view anyway. So in 2D or 3D, this will change the direction of objects relative to the observer as well. If you're driving down a highway, you're just in one direction, so the car will be moving forward or back, and from anyone else's point of view, it will also be moving forward or back across the ground. But if someone else is moving in a different direction, say at an intersection, then this will change the direction that they perceive the car to be moving in. So let's look at an example of relative motion. Suppose we've got a car moving at 12 meters per second north. We can see that at the bottom of this picture. The car in front changes lanes. It moves at 13 meters per second, which is a little faster, at an angle 22.62 degrees east of north. So we can see that in around the middle of the picture. Now we can use vector subtraction to find how fast the middle car appears to be moving to the back car. So let's take a look at the vector subtraction of that. So here we have our triangle. We have the 12 meters per second being subtracted meaning it's pointing in the opposite direction that the car was moving. And we have the 13 meters per second up in this direction. Now just a hint, this is a right-angled triangle. It's in fact a Pythagorean triplet, which means that this bottom number is an integer. It's very useful for us. Now, the magnitude of the resultant vector, that is, the green vector, we can find with Pythagoras' theorem, c squared equals a squared plus b squared. Or if we're not finding the hypotenuse, a squared equals c squared minus b squared, where c squared is the hypotenuse. So, substituting in our 12 and 13 meters per second, we have a squared is 13 squared minus 12 squared. 13 squared ends up being about 169, and 12 squared is 144. And so, subtracting one from the other, we find that this is 25. And so, a is the square root of 25, which is, of course, 5 meters per second. So that's the magnitude of the vector. Right, well, what about its direction? We know it's a right-angled triangle, and so it's due east from north. And this means that the car in front of us that's changing lanes doesn't appear to be moving towards us or away from us at all. It's just moving sideways as it changes lanes. I'm sure it's consistent with what many of you have seen on the road when another car changes lanes in front of you. It doesn't really move toward you or away from you, it just sort of moves across. So that's what relative motion looks like. This ends the theory. So we've learned about various ways to apply vectors to physical situations, as well as how to apply them to relative motion to find out what an object looks like relative to another. Let's go on to some questions. Question 6. We usually use the surface of the Earth as a frame of reference in physics, but what is the universe's absolute frame of reference? Let's go through the options. Is it the center of the sun? Well, that can't really be right because the sun orbits the center of the galaxy, so we can say that relative to some other frame of reference, it's moving. Alright, well, what about the center of the Milky Way? Well, the Milky Way, which is our galaxy of course, is just one of the many galaxies in the local galactic group, so we can say it's moving relative to the center of mass of the local galactic group. It's not really an absolute frame of reference. Well, could it be the local galactic group then? No, there's nothing special about the local galactic group, except it's not that we're in. There are lots of other galactic groups out there, and they all have their own center of masses. So, is it the center of mass of all the local galactic groups, or... well, that doesn't really work either. In fact, our answer is that there are no absolute stationary frames of reference in the entire universe. So whenever we measure motion, we have to measure it relative to something else. And so we find that D is the right answer. There is no absolute frame of reference in the universe. Question 7. Two cars are moving toward each other, each moving at a constant speed of 20 meters per second, relative to the Earth's surface, of course. So we have one car here with two wheels moving that way, one car here with two wheels moving that way. Now, which is correct? Is it A? The cars are not moving relative to each other. Well, if they were moving in the same direction, this would be true, and that's why cars don't appear to move when you're traveling behind another car on the highway. But if they're moving towards each other, this isn't the case. Well, could it be B then? The cars are moving at 20 meters per second relative to each other. That's not the case. If we're standing on the Earth's surface and we're saying that we're stationary, then each of them is moving at 20 kilometers per hour to us. And so if one car was stationary, then each would see the other moving at 20 meters per second. But because they're both moving together, this isn't the case. Could it be D, none of the above? No, it couldn't. And the reason for that is because it's C. The cars are moving at 40 meters per second relative to each other. Remember that if we take the observer's motion and we subtract it, we can find what they perceive the motion to be. So subtracting 20 meters per second looks like that, because the 20 meters per second was originally in the other direction. And so we can see that the other car perceives this one to be moving at 40 meters per second. Because of course, subtracting a negative number is the same as adding a number. And if we do that to the other car, we'll see that it perceives the other car to be moving at 40 meters per second as well. So, the correct answer is C. The cars moving at 40 meters per second relative to each other. Question 8. What is the bearing from the port to the ship? The port being at the bottom, the ship being at the top. We can see that the ship has moved 1 nautical mile north, then 1 east, and then 2 nautical miles north again. And so what we end up with is this green resultant vector. we can draw a bit of a right angled triangle here with side lengths 1 and 3 on this side here. And because we have a right angled triangle, we can do trigonometry to it. So we find that theta, that is the angle that it's at, is tan of 1/3, because of course it's the tan of the opposite, 1 nautical mile, over the adjacent, which is 3 nautical miles. Putting that into a calculator, we can find that the theta is 18.43 degrees. So the bearing of the vector is from north 18.43 degrees, and so we have north 18.4 degrees east. So the bearing is north 18.43 degrees east. Well, what about the magnitude? So if we find the magnitude of this vector, we'll find the distance from the port to the ship. So we can use the Pythagoras' theorem for that. C squared equals A squared plus B squared. A squared and B squared are of course the 1 nautical mile and the 3 nautical miles. And so we find that 1 squared plus 3 squared equals 10, and that's the value of C squared. Finding the square root of that will give us what C is. So if that advances the slide there. There we go, the square root of 10, which of course evaluates to be 3.16 nautical miles. And that means that we can describe this vector by saying both its bearing and its magnitude, which is the 3.16 nautical miles. Question 9. From our frame of reference at a space station, spaceship A approaches spaceship B at a right angle. So we can see that from our point of view in the space station, spaceship A is moving at 4 kilometers per second, spaceship B is moving at 3 kilometers per second, which is quite fast, but you know, they're spaceships. So. All right, so how fast is A moving relative to B? Well, we can solve this by using vector subtraction. So we subtract B's velocity, which is the blue one there, from A's velocity, forming a right angled triangle. So we can see that after adding the vectors together, we end up with this green resultant vector, which luckily is right angled. Because it's a right angled triangle, we can use Pythagoras' theorem to figure out exactly the magnitude of the hypotenuse. So we can use C squared equals A squared plus B squared, where we have C, A, and B. Maybe A and B are the other way around. Doesn't matter. Which of course is 4 squared plus 3 squared. And so that equals 25. We know that the square root of 25 is 5. So the hypotenuse here is simply 5 kilometers per second. And that's how fast A appears to be moving from B's frame of reference. Part B. Spaceship A launches a missile at 1 kilometer per second relative to A. How fast is the missile moving relative to us if it's moving in the same direction as A? Well, from A's point of view, it's firing a missile moving that direction at 1 kilometer per second. And so if A weren't moving, it'd be moving at 1 kilometer per second, but because A is moving across at 4 kilometers per second, we can actually add the kilometer per second of the missile to A's velocity. And so we find that if we add A's velocity to the relative velocity of the missile relative to us is moving at 5 kilometers per second. Another way we can think of this is working from A's frame of reference. From A's frame of reference, we, the space station, the observer, is moving in the opposite direction at 4 kilometers per second. And then subtracting our observing velocity from the 1 kilometer per second missile means that we reverse this because we're subtracting, and adding these two vectors together, 4 and 1, also produces the 5 kilometers per second. That is the correct answer. Now, on to the last question. Question 10. The Earth's daily rotation causes its surface to move at about 465 meters per second relative to its axis of rotation. It's pretty fast. So, part A. An aeroplane is traveling at 240 meters per second relative to the Earth's surface. So, here's the Earth's surface. Here's the plane, sort of traveling at 240 meters per second relative to us standing still on the ground. Now, if the aeroplane is moving in the same direction as the Earth's rotation, how fast is it moving relative to the axis of rotation of the Earth? Well, this means that we're not viewing this from our little perspective here on the ground. We're viewing it from a sort of stationary frame of reference that's in the middle of the Earth that's not rotating. So in this case, we'll be adding our observing velocity, which of course is 465 meters per second, to the plane's velocity. And so relative to the stationary axis of the Earth, we add these two numbers together to find that the plane, relative to that, is moving at 705 meters per second, which is, mind-bogglingly fast. But of course, they won't notice that because the air is moving at the same rate as the Earth's surface. So if it were moving in the opposite direction, obviously this number would be much smaller. So the speed of planes is measured relative to the air around them, which is the same as the surface. If it was measured relative to the axis of rotation of the Earth, you get very different numbers indeed. And in fact, close to the North Pole and the South Pole, the Earth's surface doesn't really move very fast at all. And so this number would change again. 465 meters per second is the speed of the Earth's surface close to the equator. Now, part B. A very fast aircraft flies in the opposite direction to the Earth's rotation at 600 meters per second relative to the Earth's surface. How fast is it moving relative to the Earth's axis of rotation? Well, let's think about this. Here's the Earth. We can say it's rotating around this way. And our plane is going against the motion of the Earth's rotation. So, it's flying in that direction. Now, this number is 465, that's the rotation of the Earth, but the plane is moving at 600. So the plane speed actually exceeds the surface of the Earth relative to the Earth's axis of rotation. So that means, rather than adding the two numbers together, we'll be subtracting the larger number from the smaller number. And that means that we get a negative number. And so we get 465 minus 600 is 135 meters per second against the direction of the Earth's rotation. And now it's the Earth's rotation that causes us to look at the sun rising and the sun setting. So if you're moving against the direction of the Earth's rotation, it means that the crew of the aircraft would outspeed the setting sun. They would perceive the sun rising in the east much slower than it, so they'd observe it setting in the east and rising in the west, and will be at a much slower rate because they're only moving at 135 meters per second rather than our 465. This concludes the questions. In this section, we've learned about how to apply vectors to real-world situations, including describing velocity and displacement, and being able to find out relative motion between two objects.